So hello everyone, today we'll be discussing the GFG PoTD, which is check whether the BST contains a dead end, and this is a easy level problem. So you will be given a binary search tree which consists of unique positive integer values, and you want to check if the BST contains a dead end. So what is a dead end? A dead end is a leaf node at which no node can be inserted. So you should pause the video and try the problem first yourself to have better understanding of what the problem states. Cool. So let's just take this test case first. So in this test case you can see that here you are given that 1 is a dead end. So why 1 is a dead end? Because you cannot insert anything at the left of 1 and anything at the right of 1. So anything at the left of 1 will be less than 1, anything will be right will be greater than 1. So if you see the parent of 1, which is 2, so anything which is greater than 1 is also greater than 2. So you can just put it to the right of 1, and there cannot be any node less than 1 because the problem states that we are going to put positive values, and also the value of nodes is always greater than 1. So you cannot put, so 1 is a dead end in this situation. So if we can write the conditions for a dead end, so first if our node value is equal to 1, so this is our first condition for a dead end. Okay, now let's just look at the second test case. Sorry about that. Cool. So take this. Yeah, so try to figure out the dead end for this. So if you check, 9 is a dead end in this condition, in this test case. Why? Because if you iterate on the binary tree, you cannot put anything at the left of 9 and anything at the right of 9, because if you look at the parent, or if you look at the interval in which 9 is put, the 9 is in the interval of 8 and 10. And how did I find the interval thing? Okay, so let's say you are on the root node, your interval is minus infinity to infinity, because you can put anything as node. So in your binary tree you can have all the numbers, right? Now let's say I put 8 as the node. This interval breaks into 2, because in the left tree you can only have minus infinity to 8, and in the right tree you can have 8 till infinity. Of course you cannot have the equality sign on either infinity or 8, because 8 is already root node. Now let's say this 7 comes. Now in 7 this interval breaks further to minus infinity to 7, because in the left we can have this, and in the right we can have 7 to infinity. So I guess you know there is no value like that here, so I'll not make it, but I think you get the idea that the interval keeps splitting. Now let's talk about what happens in case of 9 and what specifically changes. Cool. So let's say you have 8 till infinity here. Okay, now here at 10 the interval splits again. So in the left of 10 you can have 8 to 10, in the right of 10 you can have 10 to infinity. So the interval breaks again, right? And here you have 13. So we are not going to talk about 13, because it is quite obvious that 13 is not a dead end, because when you split it you can have 10 till 13 values in the left subtree, and in the right subtree you can have 13 to infinity values in the right subtree. Okay, let's talk about this node. So 9, if you talk about this interval, so there is only one value which can be put in this interval, because the size of this interval is 1. Only one value which can be put is 9. So I think that you can make the second observation, that size of the interval is 1. And how do you calculate the size of the interval? So you can just give two values in your DFS function, R and L, which denotes the lower bound and the upper bound of this function interval. So let me just explain you through the example of a code, not this. Yeah, so I have just taken the DFS function and my flag bit. So my flag bit is initially true. True means that I haven't found a dead end, but if I find a dead end we will just put it as false, and I just return the not of flag. Okay, if our node is not there, like if our node is null or something, then we return it, because we don't see anything. Now this is the main condition. this is our first condition and this is the second condition. So whenever I am applying this condition, when the left node is null, the left and the right is null. So this signifies the leaf node condition of our node. So if our node is leaf node, then we are going to enter in this if. So if our node value is 1 or the size of the interval is 1. So I just explain you the interval thing. So this is only doing that. In the initial I am taking minus int min and then I am taking int max for the right interval. So and I am also changing the intervals like this. You can see. So L becomes the same and node data becomes the new upper limit for our left subtree. Similarly for our right subtree, we are going from node data to R. So for our right subtree, we can only have values greater than node data and less than R. So if the value of interval is 1, then we can do the flag false and hence we have found a dead end also. So I hope you understood the solution. If you have any problems, you can comment it down, and thanks for watching.